Hello, everyone. In this video, we will learn about double integrals. Double integrals. These are integration of a continuous function over a region of integration in two dimensions. Suppose there is a continuous function defined over a rectangular region. Double integrals are used to compute physical quantities defined on the region. For a point in the region, let the differential area be the area of this subregion containing the point. The area of the entire region is the double integral of the differential area. Meanwhile, suppose this plane is a transformation of the subregion onto the point in the surface, where these partial derivatives are the slopes of the plane in the x and y directions. So the area of the surface is the double integral of the transformation of the differential area onto the surface. And for the solid object formed by the surface, the region of integration, and the sides between them, the volume of the object is the double integral of the variable height from the surface to the region of integration times the differential area. These physical quantities will be the topics in the next videos. In the following discussions, we will learn the definition and computing double integrals. Definition of double integrals. Let us start with defining the region of integration. The simplest region of integration for double integrals is a closed rectangular region defined as an interval in two dimensions. Suppose this surface is the graph of a function of two variables, and we want to compute the double integral over a closed rectangular region, which is the rectangle formed between, and including, two numbers along the x and y directions. The region of integration can also be written as the following set of points whose coordinates satisfy a couple of inequalities. Meanwhile, this is the part of the surface that covers the rectangular region, which can be written as the following set of points such that the given function is satisfied and the point is in the rectangular region. Then divide the region into equal subregions. In the x direction, let delta x be the length of each subinterval, and m as the number of subintervals. So delta x is given by this expression. In the y direction, let delta y be the length of each subinterval, and n as the number of subintervals. So delta y is given by this expression. Focus on one of these subregions, where delta A is the area of a subregion, and it is equal to the product of delta x and delta y. Next, let us represent the subregion using a sample point. A sample point is a point in a rectangular subregion. In the figure, a sample point can be this point in the middle of the subregion. The subregion and the corresponding portion of the surface form an element of the solid. For the eth subinterval in the x direction, and the jth subinterval in the y direction, each coordinate of the sample point using the midpoint rule is just the middle number between the corresponding boundaries of a subinterval. Before going any further, note that I goes from 1 to m, while j goes from 1 to n. So x0 is a, xm is b, y0 is c, and yn is d. Now, aside from using the midpoint of a subregion as the sample point, other points in the subregion that are easily represented can be used as a sample point too. Look into this side of the illustration. The upper right point is this point in the subregion. The upper left point is this point in the subregion. The lower right point is this point in the subregion. And the lower left point is this point in the subregion. Each sample point corresponds to a point in the surface. Sample volume. For a function of two variables, an elemental volume is approximated as the volume of a representative rectangular parallelepiped whose base is a subregion of the region of integration. The height of the rectangular parallelepiped is determined by the value of the function at the sample point. So a sample volume is the volume of a rectangular parallelepiped of whose height is the value of the function at the sample point. So the volume of the rectangular parallelepiped is the product of its height and the area of the subregion. Recall that for a function of one variable, its Riemann sum over a closed interval is the sum of sample areas, and it is used to approximate the area of a plane region under a curve. Double Riemann sum. It refers to the sum of sample volumes that cover the region of integration. Fill the region with rectangular parallelepipeds along the x direction. And then fill the region with rectangular parallelepipeds along the y direction. So for a function of two variables, a double Riemann sum approximates the volume of this solid region. And it is defined by this double summation. Note that the result is the same if the region is covered along the y direction first and then along the x direction next. The height of the rectangular parallelepipeds are affected by which sample point is used. This is what it looks like when midpoints are used. A rectangular parallelepiped reaches its height when the midpoint of its top side touches the surface. For upper right sample points, a rectangular parallelepiped reaches its height when the upper right corner of its top side touches the surface. For upper left sample points, a rectangular parallelepiped reaches its height when the upper left corner of its top side touches the surface. When the sample points are in the lower right corner, a rectangular parallelepiped reaches its height when the lower right point of its top side touches the surface. And when the sample points are in the lower left corner, a rectangular parallelepiped reaches its height when the lower left point of its top side touches the surface. Regardless of which sample point is used, as the size of the rectangular subregions are decreased, more rectangular parallelepipeds can be used to approximate the shape of the entire solid. Hence, the double Riemann sum represents the approximate volume under a surface. Recall that for a function of one variable, its definite integral over a closed interval is the limit at positive infinity of the corresponding Riemann sum. Next, let us establish the definition of the double integral. Suppose a function of two variables is continuous over a closed region of integration. For each point in the region, the differential area is the area of an infinitesimal region containing the point, while the value of the function at that point is the height of the infinitesimal solid. Then the double integral of the function over the region of integration is the limit at positive infinity of the corresponding double Riemann sum. That is, the double integral is the double Riemann sum when the elements of the solid are very small. If this limit exists, it means that the function is integrable. Double integral as volume. We have just developed the definition of double integrals by computing the volume between a surface and the region of integration. But let us be more specific when this is applicable. If a function is non-negative and integrable. Non-negative means the function is greater than or equal to 0, which means the surface lies on or above the xy plane. Then the double integral of the function over the region of integration is the volume between the surface and the region of integration. Hence, this double integral is the volume under a surface. However, if a function is just integrable, and there is no restriction on its value, which means the surface lies on, above, or below the xy plane, then the double integral of the function over the region of integration is the net volume between the surface and the region of integration. Net volume means volume above minus volume below. Thus, this double integral is the net volume bounded by a surface. For such a case, the surface intersects the xy plane and divides the region of integration. The double integral of the non-negative portion of the function is going to be positive, while the double integral of the negative portion of the function is going to be negative. The sum of these two double integrals leads to the net volume bounded by the surface. Evaluating double integrals. The definition of double integrals involves the limit at positive infinity of a double Riemann sum. However, there is a more convenient way to compute double integrals by converting it to iterated integrals. The strategy is to integrate on the entire region by sweeping in the x direction and then in the y direction, or vice versa. The region of integration sets the limits of integration in the x and y directions. If we sweep in the x direction first, the result is a cross-section of the solid whose area is given by the following single integral, where y is treated as a constant because every point on the cross-section would have the same value of y. But x changes, so it is the variable of integration. And this is partial integration with respect to x. To cover the entire region of integration, let us sweep in the y direction next. The result is a series of cross-sections of the solid, for all values of y from c to d, whose area changes depending on the value of y. Y changes, so it is the next variable of integration. Therefore, the double integral is written as iterated integrals, which is evaluated starting at the inner integral and then proceeding with the outer integral. If we sweep in the y direction first, the result is a cross-section of the solid whose area is given by the following single integral, where x is treated as a constant because every point on the cross-section would have the same value of x. But y changes, so it is the variable of integration. And this is partial integration with respect to y. To cover the entire region of integration, let us sweep in the x direction next. The result is a series of cross-sections of the solid, for all values of x from a to b, whose area changes depending on the value of x. X changes, so it is the next variable of integration. Hence, the double integral is written as iterated integrals, which is evaluated starting at the inner integral and then proceeding with the outer integral. Please watch the video of examples about applications of double integrals in computing area and volume. Thank you for watching. Please like this video and subscribe to Professor Reginald's channel to get the latest updates.